Hello there. Come on in and make yourself comfortable. You found Science Blanket, and I'm so happy you've decided to spend these quiet moments with me. Have you ever stood by the shore and wondered why the ocean never seems to sleep? Even when the air is perfectly still, the water is always moving, rising, and falling as if it's following a secret, ancient pulse. Tonight, we are wrapping ourselves in the mystery of the moon and the tides. It is a silent, cosmic tug-of-war that has been happening for billions of years, a story where a silver rock hanging in the velvet dark reaches out with invisible hands to literally lift the world's oceans. We aren't just talking about water, we are exploring the rhythm that keeps our planet steady and guides the lives of everything from the smallest coral to the great blue whale. As we begin, imagine yourself sitting on a soft, sandy dunes at midnight. The waves are whispering against the shore, moving with a rhythm so steady you can feel it in your own chest. You don't need to calculate the gravity or worry about the math of the moon's orbit tonight. Just let the rise and fall of the tide tuck you in like a gentle, rhythmic breath. If this blanket of moonlight and salt air helps you find rest, I'd love for you to subscribe and join our community of sleepy explorers. It helps us keep this quiet space open for everyone searching for a peaceful night. Now, let's take a slow, deep breath together. As you exhale, feel your body becoming heavy, as if you are sinking into the warm, supportive sand. Release the tension in your shoulders, let your eyelids grow heavy, and allow the day's noise to be washed away by the incoming tide. You are safe, you are still, and the moon is watching over the world for you. Let's explore the quiet power of the tides together. The moon hangs in our sky, distant and serene, yet its influence reaches down across the void of space to shape the very oceans that cover our planet. It's a connection that spans nearly 240,000 miles, an invisible thread of gravity that pulls and tugs at the waters below. When we stand at the shore and watch the tide roll in, we're witnessing something extraordinary, a cosmic dance between two celestial bodies that has been unfolding for billions of years. The moon's gravity doesn't just illuminate our nights. It reaches out and literally reshapes the surface of our world, creating forces so persistent and so powerful that they move entire oceans twice a day, every day, without pause. Imagine the Earth floating in space, wrapped in its blue cloak of water. Now imagine the moon nearby, its gravity reaching out like an invisible hand. That gravity doesn't pull evenly on everything. It pulls hardest on whatever is closest to it, and this simple fact creates something beautiful and strange. On the side of Earth facing the moon, the ocean water feels that pull more strongly than anything else. The moon's gravity tugs at those waters, drawing them outward, stretching them toward the lunar surface above. The ocean responds, rising up, creating a bulge of water on the side of the planet that faces our celestial companion. This is the near-side bulge, a dome of elevated ocean that follows the moon as Earth turns beneath it. But here's where it gets truly fascinating. There isn't just one bulge. There are two. While the near-side bulge makes intuitive sense, the moon's gravity pulling water toward it, there's another bulge on the exact opposite side of Earth, the side facing away from the moon, the side that seems like it should be pulled least of all. This far side bulge seems to defy logic at first, but it exists for a reason that reveals just how subtle and profound gravitational forces can be. The key is understanding that the moon isn't just pulling on the ocean. It's pulling on everything: the water, the air, the rock, the molten core, all of it. But it pulls on different parts of Earth with different strengths. The moon pulls Earth itself, the solid planet beneath the oceans, more strongly than it pulls the water on the far side. Think of it this way. The moon grabs Earth and pulls it slightly toward itself, but the ocean on the far side doesn't get pulled quite as hard because it's farther away. So while Earth gets tugged moonward, the water on the far side gets left behind, relatively speaking. It's not that the far side water is being pushed away. It's that Earth is being pulled away from it. The result is the same, a bulge of water on the side of the planet opposite the moon, mirroring the bulge on the near side. Two bulges, two high tides, created by a single gravitational relationship. This differential pull, this variation in gravitational force across Earth's diameter, is what we call a tidal force. It stretches Earth along the line connecting our planet to the moon. Imagine pulling on opposite ends of a piece of clay. It elongates, stretching along the axis of force. Earth does the same thing, but instead of clay, we're talking about rock and water and air. The planet itself deforms under this influence, though we rarely think about it. We imagine Earth as solid and unchanging, but under the moon's persistent pull, even the rocky crust beneath our feet rises and falls. The solid ground you're standing on right now is being lifted and lowered by as much as 30 to 40 centimeters throughout the day. Nearly 1.5 feet of vertical movement in the very bedrock of the planet, and we never feel it because it happens so gradually, so smoothly, affecting everything around us equally. But while rock can bend and flex under this tidal force, it does so slowly and subtly. Water is different. Water is fluid, responsive, eager to move. Where rock might rise 30 centimeters, the ocean can rise meters. The water doesn't fight the pull. It flows with it, gathering into those two great bulges that encircle the planet. High tides occur wherever these bulges are located at any given moment. If you're standing on a beach where one of these bulges is passing, you'll see the water rise, creeping up the sand, claiming territory it didn't hold just hours before. The tide comes in not because water is being created or added to the ocean, but because water from elsewhere is flowing to where you are, piling up in response to the moon's call. Between the two bulges, in the regions perpendicular to the Earth-Moon line, the opposite happens. Water flows away toward the bulges, leaving less behind. These are the low tides, the moments when the ocean retreats, when tide pools appear, when the beach extends farther than it did that morning. The water hasn't disappeared. It simply moved to where the gravitational pull directs it, gathering at the bulges while leaving the areas in between depleted. As Earth rotates on its axis, spinning through day and night, it rotates through these bulges. A point on Earth's surface passes through a high tide, then a low tide, then another high tide, then another low tide, in a rhythmic cycle that has governed coastal life since the oceans first formed. You might expect this cycle to take exactly 24 hours, matching Earth's rotation. But it doesn't. The cycle takes 24 hours and 50 minutes. That extra 50 minutes is crucial, a small detail that reveals a deeper truth about the relationship between Earth and Moon. While Earth spins on its axis, completing a full rotation every 24 hours, the Moon isn't standing still. The Moon is orbiting Earth, moving in the same direction that Earth rotates. In the time it takes Earth to complete one full spin, the Moon has moved a bit farther along in its orbit. So Earth has to rotate just a little bit more, for about 50 extra minutes, to catch back up to where the Moon is now positioned in the sky. This means the tidal bulges, which are always aligned with the Moon, also shift slightly. The cycle of tides follows the Moon's position, not just Earth's rotation, which is why high tides don't occur at the same time every day but arrive about 50 minutes later each day. This is the fundamental mechanism behind the tides, a phenomenon so vast and so regular that ancient peoples built calendars around it, navigated by it, structured their lives along its rhythms. Two bulges of water, one facing the moon and one facing away, stretched across the planet by the differential pull of lunar gravity. Two high tides and two low tides every 24 hours and 50 minutes, as Earth rotates through these bulges and the moon continues its ancient orbit. The solid Earth itself rising and falling by dozens of centimeters, while the fluid oceans respond far more dramatically, rising by meters. All of it driven by a companion world nearly 250,000 miles away, proof that nothing in the cosmos exists in isolation. Everything pulls on everything else. Everything influences everything else. And as you lie here listening, the moon is out there right now, pulling at the oceans, shaping the tides, continuing a gravitational conversation that has been ongoing for 4.5 billion years. When we think about the forces that govern our world, the sun naturally comes to mind first. It's massive beyond comprehension, containing more than 99% of all the mass in our solar system. Earth orbits it because its gravitational pull is so overwhelming that nothing nearby can escape its influence. The sun holds us in place, keeps us warm, gives us light, powers virtually everything that lives and grows on our planet. So it might seem natural to assume that the sun, being so much larger and more massive than the moon, would be the dominant force shaping our tides. But nature has a surprise in store. The moon, our small rocky companion, actually exerts a tidal force on Earth about twice as strong as the sun's. Despite being dwarfed in size and mass by our star, the moon is the primary conductor of the tidal symphony. The reason for this apparent paradox lies in one of the more subtle aspects of gravity. Tidal forces don't follow the same rules as ordinary gravitational attraction. When we talk about the force between two objects, like Earth and the Sun, we usually think about the inverse square law. Gravity gets weaker with the square of the distance. Double the distance, and the force becomes 1/4 as strong. But tidal forces are different. They depend not on the total gravitational pull, but on how much that pull varies from one side of an object to the other. Tidal forces follow an inverse cube law. They decrease with the cube of the distance, not the square. Triple the distance, and the tidal force doesn't become 1/9 as strong. It becomes 1/27 as strong. Distance matters enormously when it comes to tides, far more than mass does. The Sun is about 27 million times more massive than the Moon. That's an almost incomprehensible difference. But the Sun is also about 390 times farther away from Earth than the Moon is. When you apply the inverse cube law, that distance factor crushes the mass advantage. The Sun's greater mass can't overcome its greater distance. The Moon, being so much closer, creates a steeper gravity gradient across Earth's diameter. The difference between the Moon's pull on the near side of Earth and its pull on the far side is greater than the corresponding difference created by the Sun, even though the Sun's total gravitational grip on Earth is far stronger. This is why the Moon dominates the tides. Proximity wins over mass when it comes to stretching worlds. We can even measure the Moon's tidal influence precisely. The lunar tidal acceleration at Earth's surface, the actual force per unit mass that the Moon's gravity gradient produces, is about 1.1 times 10 to the -7th g. That's a tiny number, a mere 10 millionth of Earth's surface gravity. Stand on a scale and you won't notice it. Jump and you won't feel it. But apply that seemingly negligible force to an entire ocean, to trillions upon trillions of tons of water, and it becomes profound. The tidal force is weak at any single point, but it acts everywhere simultaneously, across the entire planet, accumulating its effect. Water rises where the force directs it, creating those bulges we discussed before, the high tides that sweep around Earth twice a day. The Moon's tidal force creates what physicists call a gravity gradient, a smooth variation in gravitational pull from one location to another. On the side of Earth nearest the Moon, the pull is strongest. On the far side, it's weakest. In between, it's somewhere in the middle. This gradient is what stretches Earth, what pulls the oceans into their elongated shape. It's a persistent, unrelenting force, acting every moment of every day, never pausing, never weakening, as reliable as the Moon's presence in our sky. And because the Moon orbits Earth while Earth rotates, this gravity gradient sweeps around our planet, dragging the tidal bulges with it, creating the rhythm of high and low tides that coastal communities have lived by for millennia. But here's where the story becomes even more interesting. Those tidal bulges don't align perfectly with the Moon. You might expect them to point directly toward and away from the Moon at all times, following it exactly as Earth rotates. But they don't. Earth's rotation interferes. As Earth spins beneath the Moon, friction between the ocean and the seafloor, between water and land, drags on the tidal bulges. Earth tries to carry the bulges along with it as it rotates, pulling them ahead of where they would naturally want to be. The result is that the tidal bulges lead the Moon's position by about 5 to 10 degrees. They're slightly ahead, offset from the direct Earth-Moon line, carried forward by Earth's rotation like water sloshing in a turning bucket. This offset, this misalignment between the bulges and the Moon, creates something remarkable. It creates tidal drag, a friction between Earth and Moon that has profound consequences for both bodies. The bulges, being slightly ahead of the Moon, exert their own gravitational pull on the Moon from a position that's not quite aligned. It's like a gentle tug forward in the direction of the Moon's orbit. This speeds the Moon up very slightly. Meanwhile, the Moon pulls back on those offset bulges, and through them, on Earth itself. This acts like a brake on Earth's rotation, a cosmic friction that gradually, inexorably, slows down our planet's spin. The effect is small but measurable. Earth's rotation is slowing by about 2.3 milliseconds per century. That doesn't sound like much. In a human lifetime, you'd never notice. But it accumulates. Over millions of years, it adds up. Hundreds of millions of years ago, Earth's day was significantly shorter than it is now. Geological evidence, preserved in the growth patterns of ancient corals and in tidal sediments, shows that Earth once spun faster, that days were perhaps only 22 hours long in the distant past. The Moon has been slowing us down for eons, stealing our rotational energy bit by bit, day by day, through the mechanism of tidal friction. But energy doesn't just disappear. It has to go somewhere. The rotational energy that Earth is losing is being transferred to the Moon, specifically to the Moon's orbital motion. As the Moon gets tugged forward in its orbit by those offset tidal bulges, it speeds up. And when an orbiting object speeds up, something counterintuitive happens. It doesn't stay at the same distance. It moves to a higher orbit. The faster the Moon moves, the farther from Earth it drifts. This is orbital mechanics, one of the beautiful paradoxes of celestial motion. The moon is using the energy it steals from Earth's rotation to climb to a higher orbit, moving away from us in the process. The moon recedes at about 3.8 centimeters per year. Not quite 4 centimeters annually. That's roughly the rate at which your fingernails grow. It seems insignificant, almost laughably small. But like Earth's slowing rotation, it adds up. Over the course of your lifetime, the moon will move several feet farther away. Over 1 million years, it will retreat by 38 kilometers. Over 1 billion years, by 38,000 kilometers. The moon was once much closer to Earth than it is now. In the early days of the solar system, shortly after the moon's formation, it may have been close enough that it appeared many times larger in the sky than it does today. The tides then were monstrous, far more extreme than anything we experience now. And the moon will continue to recede, slowly climbing away from Earth for as long as the tidal dance continues, for as long as Earth's rotation provides energy to steal. This is tidal evolution, a gradual transformation of the Earth-Moon system driven by the offset of the tidal bulges. It's happening right now, as you listen to these words. Earth is spinning just a tiny bit slower than it was yesterday. The moon is just a tiny bit farther away than it was last year. The process is so slow that it's imperceptible in human timescales, but over the deep time of geology and astronomy, it has reshaped the relationship between our planet and its companion. And it will continue to do so for billions of years to come, until eventually, far in the future, Earth's rotation and the moon's orbit become synchronized, locked together in what scientists call tidal locking. But that's a story for another time. A distant future when days are much longer and the moon hangs in one spot in the sky, always visible from one hemisphere of Earth and never from the other. For now, the moon continues its slow retreat, and Earth continues its gradual slowdown, two partners in a cosmic waltz that has been choreographed by gravity and time. The tides we experience are not constant. They rise and fall twice a day. Yes, but the height of those rises and the depth of those falls changes throughout the month. Some days the high tide climbs higher up the beach than usual, while the low tide retreats farther than it did the week before. Other days the difference between high and low tide is modest, almost subtle. This variation follows a pattern, a monthly rhythm that reflects the changing positions of the moon and sun in our sky. The tides are strongest when these two celestial bodies work together, and weakest when they work against each other. It's a choreography written in the language of orbital mechanics, played out in the rising and falling of ocean waters around the world. Spring tides are the name we give to the highest and lowest tides of each month. The name has nothing to do with the season. Spring tides occur year-round, twice each lunar month, and they happen when the sun, moon, and Earth align in space. This alignment occurs during two specific lunar phases, the new moon and the full moon. During a new moon, the moon lies between Earth and the sun. All three bodies form a straight line, with the moon positioned on the same side of Earth as the sun. During a full moon, Earth lies between the sun and the moon. Again, the three bodies are aligned, but this time the moon is on the opposite side of Earth from the sun. In both configurations, the gravitational effects of the sun and moon point in the same direction relative to Earth. When this happens, the tidal forces from the sun and moon don't just coexist. They reinforce each other. The moon creates its two tidal bulges, one facing the moon and one on the opposite side. The sun creates its own pair of bulges, smaller but still significant, also facing the sun and away from it. During the alignment of spring tides, These bulges overlap. They add together. The solar bulge enhances the lunar bulge, making it larger, pulling the water even higher. The result is a high tide that rises noticeably higher than average, and when the bulges pass and the low tide arrives, it drops noticeably lower. The tidal range, the difference between high and low tide, reaches its maximum during these periods. Spring tides are dramatic. They flood areas that normally stay dry. They expose parts of the seafloor that are usually submerged. Coastal communities have always been aware of them, planning around them, because spring tides can affect navigation, fishing, and the safety of harbors and beaches. These are the tides that reveal the full power of the moon's influence, amplified by the sun's contribution. Twice a month, during the new moon and again during the full moon, the oceans rise and fall with extra vigor, responding to the combined call of our two largest celestial neighbors. But the moon and sun are not always aligned. Halfway between the new moon and full moon, during the first and third quarter phases, the sun and moon are positioned at right angles as seen from Earth. If you draw a line from Earth to the moon and another from Earth to the sun, these lines form a 90-degree angle. This configuration is called quadrature, and it produces what we call neap tides. During neap tides, the gravitational effects of the sun and moon partially cancel each other out. The moon is still creating its bulges, and the sun is creating its bulges, but now they're perpendicular to each other. The solar high tide occurs where the lunar low tide is, and vice versa. The sun tries to pull water in one direction while the moon pulls it in another. The result is a compromise, a blending of forces that produces weaker tides. The high tides don't rise as high during neap tides. The low tides don't fall as low. The tidal range shrinks to roughly half of what it is during spring tides. The difference between high and low water becomes modest, sometimes barely noticeable in some locations. If spring tides demonstrate the full strength of tidal forces working in concert, neap tides show us what happens when those forces work at cross purposes. The ocean still responds, still rises and falls, but with less enthusiasm, less dramatic change. It's a gentler time for the tides, a periodic calming that occurs twice a month, alternating with the more vigorous spring tides. This monthly cycle, from spring tide to neap tide and back to spring tide, is one of the fundamental rhythms of the ocean. It overlays the daily cycle of two high and two low tides with a longer pattern. Mariners and coastal dwellers have known this rhythm for thousands of years, long before anyone understood the physics behind it. They knew when to expect the highest tides and planned accordingly. They knew when the tides would be mild and took advantage of calmer conditions. The cycle continues today, as reliable as the moon's phases, because it is the moon's phases that drive it. Now imagine for a moment that the moon didn't exist. Picture Earth alone in its orbit around the sun, with no large satellite to pull at its oceans. The sun would still create tides. Its gravity would still stretch Earth, still create those two bulges, one facing the sun and one opposite. But without the moon's stronger tidal force, the tides would be far smaller and weaker than what we experience. Solar tides alone would produce only a fraction of today's tidal range. Instead of tides that rise and fall by meters, we might see changes of only tens of centimeters in many places. The dramatic intertidal zones we know today, those regions of coastline that are alternately flooded and exposed, would be much smaller, far less dynamic. Entire ecosystems that depend on tides would be diminished or might not exist at all. The moon isn't just influencing the tides. It's creating them in any meaningful sense. Without the moon, Earth would be a world of weak, subtle tides, barely worth noticing. But the story of tidal variation doesn't end with the monthly cycle of spring and neap tides. There's another factor that occasionally amplifies things even further. The moon's orbit around Earth is not a perfect circle. It's an ellipse, slightly oval, which means the moon's distance from Earth varies as it orbits. At its closest point, called perigee, the moon is about 363,000 kilometers away. At its farthest point, called apogee, it's about 406,000 kilometers distant. That's a difference of more than 40,000 kilometers, and because tidal forces depend so strongly on distance, this variation matters. When the moon is at perigee, its tidal force is significantly stronger than average. When it's at apogee, the force is weaker. Most of the time, the moon's perigee and apogee don't coincide with spring tides. They happen independently, on different schedules. But occasionally, perhaps a few times a year, they align. The moon reaches perigee right around the time of a new or full moon, when spring tides are already occurring. When this happens, we get what are called perigean spring tides, sometimes colloquially known as supermoon tides when they coincide with a full moon that appears especially large in the sky. These are the strongest tides of all. The moon is not only aligned with the sun, reinforcing its tidal effect, but also at its closest approach, maximizing that effect. Perigean spring tides can amplify tidal extremes by up to 20% compared to ordinary spring tides. 20% might not sound like much, but when you're talking about tides that are already several meters high, an extra 20% can be significant. It can mean the difference between a high tide that stays below the seawall and one that overtops it. It can mean flooding in low-lying coastal areas that normally stay dry even during spring tides. These perigean spring tides are rare enough to be notable but common enough to be part of the regular experience of coastal life. They're a reminder that the tides are governed by multiple overlapping cycles, the daily rotation of Earth, the monthly cycle of lunar phases, and the monthly variation in lunar distance, all combining in different ways to produce an ever-changing pattern of high and low water. The ocean is never truly still, never repeating itself exactly, always responding to the complex gravitational music played by the moon and sun as they move through their orbits. And as you rest here, that music continues, the tides rising and falling on shores around the world, following rhythms that are ancient beyond measure, patterns that will persist long after we're gone. Just as the moon's closest approach creates the strongest tides, its farthest distance creates the weakest. When the moon reaches apogee, that point in its elliptical orbit where it lies most distant from Earth, something subtle but measurable happens to the oceans. The tides don't rise quite as high. They don't fall quite as low. The currents that sweep through coastal channels and around islands lose some of their vigor. These are apogean tides, the counterpart to perigean tides, occurring when the moon is at its maximum distance of about 406,000 kilometers away. The difference in tidal force between perigee and apogee can be substantial, sometimes as much as 40%, because of that inverse cube relationship we discussed earlier. A moon that's farther away pulls less steeply, creates a weaker gravity gradient, and the oceans respond with reduced enthusiasm. Apogean tides have reduced height and weaker currents. For someone living on the coast, the effect is noticeable if you're paying attention. The high tide doesn't quite reach the marks it hit last week. The low tide doesn't expose as much beach or as many tide pools. Ships that needed to wait for high tide to enter a harbor might find they have a bit less water than they were hoping for. Tidal currents, those powerful flows of water that rush through narrows and around headlands, lose some of their strength. The difference isn't dramatic enough to halt ocean life or strand boats, but it's real, measurable, part of the constant variation that makes the tides a living, breathing thing rather than a simple mechanical oscillation. The moon breathes in and out as it orbits, growing closer and then retreating, and the tides breathe with it. But the moon's influence on tides extends far beyond the simple monthly cycles we've discussed. The moon's orbit itself is not fixed and unchanging. It shifts and wobbles and precesses over long time scales, and each of these orbital variations leaves its fingerprint in the tides. One of the most significant is the 18.6-year lunar nodal cycle. The moon's orbit around Earth is tilted with respect to Earth's equator. This tilt isn't constant. It oscillates slowly, over a period of 18.6 years, between about 18 degrees and 28 degrees. As this tilt changes, the moon's path across the sky shifts. Sometimes the moon rides high overhead at certain latitudes, creating stronger tides there. Other times it stays lower, weakening the tides at those same latitudes while strengthening them elsewhere. This 18.6-year cycle alters tidal strength globally. It changes the height of high tides and the depth of low tides in ways that accumulate over years. In some coastal regions, the difference between the peak and trough of this cycle can mean tides that are 10 or 20% stronger or weaker than average. For communities that live close to the water, especially in low-lying areas, this cycle can be the difference between occasional flooding and chronic inundation. When the lunar nodal cycle is near its peak, coinciding with spring tides or perigean spring tides, the potential for extreme high water increases. Coastal planners and engineers have learned to account for this cycle, recognizing that what seems like an unusually high tide in a given year might simply be part of a pattern that repeats every 2 decades or so. There are other orbital cycles too. Lunar apsidal cycles modulate perigean tides over time. The orientation of the moon's elliptical orbit slowly rotates, a process called apsidal precession. This changes when perigee occurs relative to the seasons and relative to the moon's nodal cycle. Sometimes these factors align to create particularly strong tides. Other times they work against each other, moderating the extremes. The result is a complex tapestry of overlapping cycles, some monthly, some yearly, some spanning decades, all interwoven to create a tidal pattern that is never exactly the same from one year to the next, even though the underlying physics remains constant. Some orbital cycles influence tides over centuries to millennia. The shape of the moon's orbit changes gradually. The tilt of Earth's axis precesses over a 26,000-year cycle. The eccentricity of Earth's orbit around the Sun varies over 100,000 years. Each of these astronomical cycles affects the strength and pattern of tides in subtle ways. Over thousands of years, the cumulative effect can be significant. Ancient shorelines, preserved in geological records, sometimes show evidence of different tidal patterns than we experience today. Scientists studying past climates and sea levels have to account for these long-term tidal variations, recognizing that the relationship between Earth, Moon, and Sun has changed slowly over deep time and will continue to change into the distant future. Remarkably, we can detect some of these long-period tidal signatures in unexpected places. Earth's seismic data, the continuous recordings of ground motion captured by seismometers around the world, contain subtle patterns that reflect tidal forces. The solid Earth, as we mentioned earlier, rises and falls by tens of centimeters under the moon's pull. This deformation isn't just vertical. It creates stresses in the crust, tiny changes in the shape of the planet that seismometers can detect. Scientists analyzing seismic data have found signals that correspond to tidal periods, not just the daily tides but also the longer fortnightly, monthly, and yearly cycles. These signals are faint, buried in the noise of earthquakes and human activity. But they are there, a reminder that the moon's influence extends even into the solid rock beneath our feet, not just the oceans above. All of this tidal motion, all of this rising and falling of water and deformation of rock, requires energy. The tides are not a free phenomenon. They're powered by the rotational energy of Earth and the orbital energy of the Moon, as we discussed with tidal drag. But that energy doesn't just transfer cleanly from Earth's rotation to the Moon's orbit. Much of it is dissipated along the way, converted into heat through friction. Tidal friction dissipates several terawatts of energy continuously. A terawatt is a trillion watts, an almost incomprehensible amount of power. For comparison, all of human civilization uses about 20 terawatts of energy. The tides are dissipating a significant fraction of that, several terawatts, constantly, day and night, every day of the year. Most of this energy loss comes from lunar tides. The stronger lunar tidal force, moving vast quantities of water across shallow continental shelves and through coastal seas, creates friction between the water and the seafloor. Water molecules rub against each other. Currents push against coastlines. All of that motion creates heat, warming the oceans ever so slightly, by an amount too small to measure directly but calculable from the known tidal friction. Some of the energy is also dissipated in the solid Earth, as the rock flexes and bends under tidal stress. Minerals slide past each other at a microscopic level, converting mechanical energy into thermal energy. This dissipation is why Earth's rotation is slowing and why the Moon is receding. The energy has to come from somewhere, and it comes from the rotational kinetic energy of Earth and the orbital kinetic energy of the Moon. The process is irreversible. The energy, once converted to heat, disperses into the vastness of the ocean and the interior of the planet, eventually radiating into space as infrared radiation. It can never be recovered, never be turned back into rotation or orbital motion. This is entropy at work, the inexorable tendency of organized energy to become disorganized, of motion to become heat, of systems to run down over time. But the scale of time involved is so vast that these changes seem almost frozen to us. Earth will continue spinning for billions of years more. The Moon will continue orbiting for billions of years more. The tides will continue rising and falling, dissipating their several terawatts of energy, gradually but relentlessly transforming the Earth-Moon system. It's a process that has been underway for most of the history of the solar system and will continue until either some external event intervenes or the system reaches a state of tidal equilibrium, where Earth's rotation is so slow that it always keeps the same face toward the Moon, and the Moon's orbit is so distant and so slow that further change becomes negligible. But that's in the unimaginably distant future, billions of years from now, long after the Sun has aged into a red giant and rendered the question academic. For now, for the foreseeable future, the tides continue their ancient work, shaping coastlines, powering ecosystems, slowing Earth's rotation, pushing the Moon away, and converting the energy of celestial motion into the warmth of the ocean's depths. When we picture the tides, it's tempting to imagine them as two stationary bulges of water sitting on opposite sides of Earth, rotating with the moon's position as the planet spins underneath. It's a useful mental model for understanding why tides happen, but it's not quite accurate. The reality is more complex and more beautiful. Tides are not static bulges. They're long-period waves, vast undulations that move through the oceans like ripples spreading across a pond, only these ripples are thousands of kilometers across and take hours to pass. These tidal waves propagate from the open ocean toward coastlines, carrying energy and momentum, bending around islands, squeezing through straits, reflecting off continental shelves, and interacting with the shape of the seafloor in ways that make the tides we experience at any particular shore highly dependent on local geography. Think of the ocean basins as enormous shallow bowls of water being gently tipped back and forth by the moon's gravity. The water doesn't stay in place. It sloshes. It flows. These tidal waves move across the ocean at speeds that depend on water depth, traveling fastest in the deep ocean and slowing as they approach shallower coastal waters. In the open Pacific, a tidal wave might travel at several hundred kilometers per hour. As it nears the coast and the water becomes shallower, it slows down, compresses, and often grows in height, the same way wind-driven ocean waves grow taller as they approach the beach. The tides you see at the shore are the end point of a journey that began far out at sea, a wave that has traveled across an ocean basin to reach you. But these tidal waves don't travel in straight lines. Earth is rotating beneath them, and that rotation introduces a force that affects anything that moves across the planet's surface. This is the Coriolis effect, the same phenomenon that makes hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. As tidal waves move through the ocean, the Coriolis forces from Earth's rotation deflect their motion. In the northern hemisphere, the deflection is to the right. In the southern hemisphere, it's to the left. This deflection means that tidal currents don't simply flow directly toward and away from the moon. They curve, they spiral, they create patterns of circulation that are far more intricate than simple back-and-forth motion. This creates rotating tidal systems around what are called amphidromic points. These are locations in the ocean where the tidal range is nearly zero. No high tide, no low tide, just a point of stillness around which the tide rotates like the center of a wheel. Imagine drawing lines of equal tidal phase radiating out from one of these points like spokes on a wheel. Along each spoke, high tide occurs at the same time, but as you move around the circle from one spoke to the next, the timing shifts. High tide rotates around the amphidromic point, progressing either clockwise or counterclockwise depending on the hemisphere and the particular ocean basin. Meanwhile, the tidal range increases the farther you get from the amphidromic point. Right at the point itself, the ocean barely moves. 100 kilometers away, there might be a modest tide. 1,000 kilometers away, a substantial one. These amphidromic systems are not just theoretical constructs. They're real features of the ocean, mapped by satellites and tide gauges, visible in computer models of global tides. Most ocean basins contain multiple amphidromic points, each one organizing the tides in its region. The Atlantic has several. The Pacific has several. Even smaller seas like the North Sea have their own. These points help explain why tides can vary so dramatically from one location to another, even locations that are relatively close together. Two ports a few hundred kilometers apart might experience high tide several hours apart because they lie on different parts of the rotating tidal system, on different spokes of the amphidromic wheel. But even beyond these large-scale patterns, Coastal geography strongly affects tidal range in ways that can be dramatic and surprising. The shape of the coastline, the depth of the water, the configuration of bays and estuaries, all of these factors influence how tidal waves behave when they arrive at the shore. Some coastlines are open and exposed, allowing tidal waves to wash in and out freely. In these places, tidal ranges might be modest, perhaps a meter or two. Other coastlines are complex, filled with islands, channels, and semi-enclosed bays. In these places, tides can behave in unexpected ways. Funnel-shaped bays can amplify tides dramatically. When a tidal wave enters a bay that narrows as it penetrates inland, the water has nowhere to go but up. The same amount of water that was spread across a wide opening at the mouth of the bay gets forced into a progressively narrower space. The tide rises higher and higher the farther inland you go. Some of the world's most extreme tides occur in funnel-shaped bays and estuaries. The Bay of Fundy, located between New Brunswick and Nova Scotia in Canada, is perhaps the most famous example. It reaches tidal ranges up to 16 meters. That's more than 50 feet, the height of a 5-story building, between low tide and high tide. Twice a day, the bay drains and fills with a volume of water greater than the flow of all the rivers on Earth combined. The reason for this extraordinary amplification is not just the funnel shape, though that helps. It's resonance between the basin shape and tidal period. Every body of water has a natural frequency at which it sloshes back and forth, like water in a bathtub. If you push the water at just the right rhythm, matching that natural frequency, the oscillations build up. Each push adds to the previous one, amplifying the motion. This is resonance, the same principle that allows a child on a swing to go higher and higher with well-timed pushes. The Bay of Fundy happens to have a natural sloshing period that's very close to the 12.4-hour period of the tides. The tidal wave arrives, pushes the water into the bay, and then retreats. By the time the next tidal push arrives, the bay is ready for it, and the effect accumulates. The tide builds to enormous heights not through a single event but through the continuous reinforcement of many tidal cycles, each one adding a bit more energy to the oscillation. This is why tides vary so widely around the world. Geography explains the diversity. The Mediterranean Sea has almost no tides because it's nearly landlocked, connected to the Atlantic by the narrow Strait of Gibraltar. Tidal waves can barely enter, and the basin is too small to develop significant tidal motion. Meanwhile, places like the Bay of Fundy or the Severn Estuary in the UK or the Gulf of Cambat in India experience some of the largest tides on Earth because their geography amplifies the tidal signal. The same moon, the same gravitational forces, but vastly different outcomes depending on local conditions. Even within a single coastline, tides can vary enormously. One beach might see tides of a meter or two, while a bay just a few kilometers away sees tides of 5 or 6 meters. Tidal currents in some channels can be ferocious, racing at speeds of several meters per second, while nearby areas remain calm. Sailors and fishermen have known these local peculiarities for centuries, learning through experience which harbors are safe at all tides and which ones require careful timing to avoid running aground. Entire communities have organized their lives around the specific tidal behavior of their particular stretch of coast, building piers at heights calibrated to local tidal ranges, scheduling work around the times of slack water when currents pause between flood and ebb. The tides are global in origin but local in expression. The moon pulls on the entire ocean, creating those long-period waves that sweep around the planet, But by the time those waves reach the shore, they've been shaped and molded by thousands of kilometers of ocean, by the Coriolis effect, by the arrangement of continents and islands, by the depth of the water and the shape of the seafloor. The tide you see at your local beach is the end result of all of these factors working together, a unique fingerprint that reflects not just the astronomical forces that create tides but also the specific geography of that place. And as you rest here, those tidal waves continue their journey, moving through ocean basins, rotating around amphidromic points, funneling into bays, rising and falling on shores around the world in patterns that are both universal and intimately local, both predictable and endlessly varied. In the narrow straits and channels that connect larger bodies of water, the tides reveal another aspect of their character. Here, the focus shifts from the vertical rise and fall of water to the horizontal rush of currents. Tidal currents can reverse direction multiple times per day in these constricted passages, creating flows that can be both powerful and predictable. As the tide rises on one side of a strait, water pours through toward the other side, flooding from high to low. Hours later, when the tide begins to fall, the flow reverses, ebbing back in the opposite direction. Some locations experience currents reversing every 6 hours, aligned with the semidiurnal rhythm of 2 high and 2 low tides per day. These reversing currents can be strong enough to challenge even powerful vessels, and navigators have learned to time their passages to work with the current rather than against it. The speed of tidal currents in narrow straits can be remarkable. In places like the Strait of Messina between Italy and Sicily, or the waters around the San Juan Islands in the Pacific Northwest, or the channels among the islands of Scotland, tidal currents can reach several knots, creating standing waves, whirlpools, and turbulent conditions that make navigation treacherous. The water rushes through like a river, carrying everything with it, only to reverse and rush back the other way hours later. This twice-daily reversal creates a dynamic environment where marine life must either anchor firmly to the bottom, hide in sheltered spots, or be strong enough swimmers to navigate the currents. The constant flow also brings nutrients and oxygen, making these strait environments rich feeding grounds for fish and other marine creatures that have adapted to life in fast-moving water. But tides don't just affect the open ocean and coastal straits. They can penetrate inland, moving up rivers in ways that sometimes become spectacular. Tidal bores form when incoming tides surge upriver, creating a wave front that travels against the normal downstream flow. This happens in rivers where the tidal range is large and the river channel is relatively shallow and funnel-shaped. As the tide rises at the river's mouth, water begins flowing upstream. But in some configurations, this incoming water doesn't just gradually raise the river level. It forms a distinct wave, a wall of water that advances upriver as a coherent front. These bores can travel for kilometers upstream, sometimes moving at considerable speed, creating a surfable wave that attracts adventurous surfers and kayakers. The Qiantang River in China produces one of the world's most impressive tidal bores, sometimes reaching several meters in height and traveling at speeds of up to 40 kilometers per hour. The Amazon River also experiences tidal bores, locally called pororoca, that can travel hundreds of kilometers inland. Even smaller rivers in places like England and France have their own tidal bores, modest compared to the giants but still remarkable demonstrations of the tide's power to push upstream against a river's natural flow. These bores are most pronounced during spring tides when the tidal range is at its greatest. Locals in bore-prone rivers have learned to anticipate them, sometimes gathering to watch the spectacle, while others take precautions to secure boats and avoid being caught unprepared by the sudden rise in water level. But the influence of tides on rivers extends beyond the dramatic phenomenon of tidal bores. Tides also influence rivers through more subtle mechanisms, particularly groundwater fluctuations. Even far inland, beyond the reach of any direct tidal flow, the periodic rise and fall of the ocean can affect the water table in coastal aquifers. As the tide rises, it pushes seawater slightly inland through underground pathways, raising the groundwater level. As it falls, the groundwater level drops. These inland effects can reach centimeters in amplitude, not large but measurable with sensitive instruments. Wells near the coast sometimes show daily variations in water level that correspond to the tides, evidence that the moon's influence seeps through the ground as well as flowing across the surface. The tides do more than just move water horizontally and vertically. They also drive vertical mixing of ocean layers, stirring the ocean in ways that are crucial for marine life. The ocean is naturally stratified, with warmer, lighter water floating on top of cooler, denser water below. Without mixing, nutrients that sink to the deep layers would stay there, unavailable to the organisms that live near the sunlit surface. But tides create turbulence, especially in shallow coastal waters and around underwater features. This turbulence breaks down the stratification, bringing nutrients from the depths up to the surface where light is available for photosynthesis. This mixing brings nutrients to the surface, elements like nitrogen and phosphorus that are essential for plant growth but often in short supply in surface waters. Upwelling fueled by tides supports phytoplankton growth, the microscopic plant-like organisms that form the base of the ocean food web. Phytoplankton needs sunlight and nutrients. Sunlight is plentiful at the surface, but nutrients are often scarce. Tidal mixing solves this problem in many coastal regions, constantly replenishing the surface waters with nutrients from below. Areas with strong tidal mixing tend to be highly productive, supporting abundant phytoplankton populations, which in turn support zooplankton, fish, seabirds, and marine mammals. Some of the world's richest fishing grounds are found in regions where tidal mixing is particularly vigorous, places where the constant stirring of the water column creates ideal conditions for life to flourish. Seamounts, those underwater mountains that rise from the ocean floor without reaching the surface, enhance tidal mixing by generating internal waves. When tidal currents flow over a seamount, they're forced upward, disturbed from their normal path. This creates waves that propagate through the ocean's interior, not at the surface but within the water column, along the boundaries between layers of different density. These internal waves can be enormous, with amplitudes of tens or even hundreds of meters, far larger than any surface wave. As these internal waves travel and eventually break, they create turbulence that mixes deep and shallow water, bringing nutrients upward and oxygen downward. Seamounts surrounded by strong tidal currents often develop rich ecosystems, attracting fish and other marine life drawn to the enhanced productivity created by this mixing. The process is invisible from the surface. You could sail over a seamount that's driving vigorous tidal mixing and never know it unless you had instruments to measure the temperature, salinity, and nutrient profiles of the water below. But the effects are profound. Satellite observations of ocean color, which reveal phytoplankton concentrations, often show bright patches of green water downstream of seamounts and other underwater features where tidal mixing is enhanced. These are ocean oases, pockets of productivity in otherwise relatively barren open water, sustained by the moon's gravitational pull interacting with the hidden topography of the seafloor. Tides, then, are not just about the rise and fall of water at the beach. They're about currents that reverse direction, about waves that travel upriver, about groundwater that pulses with the rhythm of the moon, about the stirring and mixing that brings nutrients to the surface and supports the biological richness of the ocean. The moon's gravity doesn't just pull water into bulges. It sets in motion a cascade of physical processes that shape marine environments, influence ecosystems, and create conditions for life. From the smallest phytoplankton cell to the largest whale, countless organisms depend on the mixing and stirring driven by tides. And all of it traces back to that gravitational connection between Earth and Moon, a connection that spans the vacuum of space and manifests in the movement of water, the flow of currents, the upwelling of nutrients, and the thriving of life in the ocean. The ocean is a sculptor, and tides are among its most important tools. Tides shape coastlines by moving sediment in and out of estuaries, carrying sand, silt, and clay in their twice-daily rhythm. As the tide floods, it brings sediment inland, depositing it in marshes, mudflats, and the quiet backwaters of river mouths. As it ebbs, it carries sediment back out to sea, sometimes redepositing it nearby, sometimes sweeping it away entirely. This constant movement builds and destroys, creates and erodes, shaping the boundary between land and sea in ways that are slow but relentless. Estuaries, those mixing zones where rivers meet the ocean, are particularly dynamic. Their landscapes shift with each tide, sandbars appearing and disappearing, channels migrating back and forth, the geography never quite the same from one year to the next. Tides control sand budgets on barrier islands, those long, narrow strips of sand that parallel many coastlines, protecting the mainland from the full force of ocean waves. These islands exist in a delicate balance. Sand arrives from rivers, from eroding headlands, from offshore sources. Tides redistribute this sand, moving it along the shore, building beaches on one end of an island while eroding them on the other. The sand doesn't stay in one place. It flows through the system like currency through an economy, the tide acting as banker, moving deposits from one account to another. When the sand budget is balanced, when inputs match outputs, barrier islands remain stable. When the budget tips, when more sand leaves than arrives, islands shrink, sometimes disappearing entirely over the course of decades. The erosive power of tides becomes especially apparent during storms. Storms coinciding with spring tides cause extreme erosion, combining high water with large waves to attack coastlines with exceptional violence. A storm that arrives during neap tide, when the tidal range is modest, might cause limited damage, the waves breaking on the beach but not reaching vulnerable dunes or structures. The same storm arriving during a spring tide, especially a perigean spring tide, can be catastrophic. The water starts higher, giving waves a head start. They reach farther inland, undermining cliffs, washing away dunes, flooding low-lying areas that normally stay dry. Coastal communities fear this combination, the alignment of meteorological and astronomical forces that can erase years of beach building in a single night. But the influence of tides extends beyond the coastline, beyond the visible movement of sand and water. Tides influence thermohaline circulation by redistributing dense water in ways that affect the great conveyor belt of ocean currents that circulates heat and nutrients around the globe. In polar regions, where seawater freezes, the formation of ice leaves behind saltier, denser water that sinks to the ocean floor. Tidal currents help mix and distribute this dense water, influencing where it accumulates and how it flows. In shallow seas, tidal mixing can prevent stratification, keeping the water column well mixed and affecting the formation of water masses with particular temperature and salinity characteristics. These effects are subtle, difficult to measure, But they matter because thermohaline circulation plays a crucial role in Earth's climate system, transporting heat from the equator toward the poles and influencing weather patterns across the globe. Tides also affect evaporation and ocean heat transport through their mixing action. By stirring the upper ocean, tides bring warmer water from below to the surface in some areas and pull cooler water up in others. This affects how much heat the ocean can absorb from the sun and how much it releases to the atmosphere. In turn, this influences the amount of water that evaporates from the ocean surface, feeding the hydrological cycle that brings rain to the continents. The connections are indirect and complex, part of the intricate web of feedbacks that govern Earth's climate, but they are real. Tides indirectly influence weather and climate patterns in ways that scientists are still working to fully understand and incorporate into climate models. Perhaps most surprising is that tides don't just affect the ocean and the solid Earth. Tidal forces also act on Earth's upper atmosphere, the thin gases that extend hundreds of kilometers above the surface. The atmosphere, like the ocean, responds to the Moon's gravitational pull. It bulges slightly toward and away from the Moon, creating atmospheric tides that propagate through the upper layers of the atmosphere. These atmospheric tides are difficult to observe directly, but they affect the density and temperature of the ionosphere, the electrically charged layer of the atmosphere that reflects radio waves and produces auroras. Plasma tides mirror ocean tidal patterns, with charged particles moving in response to the same gravitational forces that move water. Satellites orbiting in the upper atmosphere experience slight variations in drag as they pass through these tidal bulges, evidence that the Moon's influence reaches even into the near vacuum of space. And here's something that might seem impossible at first: Earth's gravity raises tides on the Moon itself. We think of the Moon as a dead, unchanging world, but it too experiences tidal forces. Earth is much more massive than the Moon, so the tidal forces Earth exerts on the Moon are much stronger than the forces the Moon exerts on Earth. But the Moon is solid rock, not liquid water, so how can it have tides? The answer is that rock, over long time scales and under persistent stress, can deform. The Moon's solid body flexes under Earth's gravitational pull, bulging slightly toward and away from Earth. These lunar tides reach heights of about 10 to 15 centimeters, a few inches of vertical displacement in the Moon's rocky crust. You can't see these tides, of course. The Moon's surface doesn't visibly rise and fall the way ocean water does. But sensitive instruments left on the Moon by Apollo astronauts detected these tiny movements. The Moon's body flexes as it orbits Earth, and this flexing generates a small amount of heat through internal friction, the same way bending a paperclip back and forth makes it warm. This tidal heating is minimal now, far too small to melt rock or create volcanic activity, but in the Moon's distant past, when it was closer to Earth and tidal forces were much stronger, tidal heating may have played a role in keeping the Moon's interior warm and partially molten. The same process that slows Earth's rotation and pushes the Moon away also once helped shape the Moon's internal structure and geological history. The story of tides, then, is not confined to the ocean. It extends to the land, shaping coastlines and moving sediment. It reaches into the climate system, influencing ocean circulation and heat transport. It touches the atmosphere, creating invisible tides in the thin air above our heads. It even reaches across space to the Moon, flexing solid rock in a cosmic echo of the ocean tides we see on Earth. Tides are pervasive force, a consequence of gravity and orbital motion that manifests in countless ways, some obvious and some hidden, some powerful and some subtle. They connect the ocean to the Moon to the Earth, the Earth to the atmosphere, and all of these to the broader clockwork of the solar system. And as you rest here in the quiet hours of the night, all of these processes continue. The sediment shifting in distant estuaries, the dense water sinking in polar seas, the plasma moving in the ionosphere, the moon's surface rising and falling by a few centimeters, all of it part of the endless dance choreographed by gravity. In the ancient past, when the moon was young and Earth was still settling into its current rhythms, the relationship between these two worlds was far more intense than it is today. The moon orbited much closer, perhaps only 20,000 or 30,000 kilometers away instead of the 384,000 kilometers that separate us now. At that distance, tidal forces were immense, hundreds of times stronger than they are in the present day. Earth's tides would have been monstrous, rising perhaps hundreds of meters, drowning and exposing vast stretches of coastline with each cycle. But Earth wasn't the only body feeling these forces. Lunar tides once generated internal heating in the moon, far more heating than the minimal amount produced today. The moon's rocky body flexed dramatically under Earth's powerful gravitational pull, bending and deforming with each orbit. This constant flexing created friction deep within the moon's interior, converting mechanical energy into heat, warming the rock, perhaps even melting it in some regions. Early tidal heating may have reshaped the moon's crust in fundamental ways. The heat generated by tidal flexing could have kept the moon's mantle partially molten for longer than it would have stayed warm from radioactive decay alone. This extended period of internal activity might have allowed magma to rise to the surface, creating the vast lava plains we now call the Lunar Maria, those dark patches visible to the naked eye that form the face of the man in the moon. Tidal heating may have influenced which parts of the moon's crust were weak enough to fracture and allow lava to flow through. The asymmetry in the moon's structure, the fact that most of the Maria are on the near side facing Earth rather than the far side, might be partly explained by stronger tidal effects on the near side where Earth's pull was most intense. The moon's geology carries the scars of its tidal past, written in frozen lava and ancient craters. As billions of years passed and the moon gradually receded, the tidal forces weakened, but they left another legacy. Earth and moon became tidally locked over billions of years, reaching a state where the moon's rotation period exactly matches its orbital period. The moon now keeps one face permanently toward Earth, rotating once on its axis in the same time it takes to complete one orbit. This isn't a coincidence. It's the inevitable result of tidal friction. Early in its history, the moon probably rotated faster, showing all of its faces to Earth as it orbited. But the tidal bulge Earth raised on the moon acted as a brake, creating drag that gradually slowed the moon's rotation until it synchronized with the orbit. Once that happened, the bulge could align with Earth and stay aligned, ending the process. This is tidal locking, and it's common in the solar system. Most large moons are tidally locked to their planets, their rotation captured by the same process that captured the moon's. From Earth, this means we always see the same lunar features. The same craters, the same Maria, the same patterns of light and dark. The far side of the moon remained a mystery until spacecraft first photographed it in 1959. For all of human history before that moment, half the moon was invisible, forever turned away from us, hidden by the tidally locked rotation. Earth is not yet tidally locked to the moon, but it's heading in that direction. Eventually, billions of years from now, Earth's rotation will slow enough that it too will keep one face toward the moon. When that happens, the moon will hang motionless in the sky as seen from one hemisphere of Earth, never rising or setting, while the other hemisphere will never see the moon at all. But this lies so far in the future that the sun will have aged dramatically by then, rendering the question moot. Long before anyone understood the physics of tidal locking or the mechanics of orbital evolution, people knew about tides. Ancient observers noticed the moon-tide connection, recognizing that the height and timing of tides followed the moon's movements across the sky. This wasn't universal knowledge. Tides are minimal in enclosed seas like the Mediterranean, so Greek and Roman writers who lived along those shores sometimes seemed confused about tides, treating them as strange phenomena that occurred in distant waters. But cultures that lived along open coasts with significant tides understood the relationship. Greek explorers linked tides to lunar phases over 2,000 years ago, noting that the highest tides coincided with the new and full moons, what we now call spring tides. They didn't know why, but they knew it was true, confirmed by generations of observation. Before clocks, sailors used the moon to predict tides, developing intuitive rules that worked even without precise measurements. They knew that high tide followed the moon's passage across the sky, delayed by a few hours that varied from place to place. They knew that tides repeated roughly every 12 hours and 25 minutes, half of the lunar day. They learned the particular timing of their home port, memorizing the local delay between moonrise and high tide, and used this knowledge to plan voyages. A sailor approaching an unfamiliar harbor at night might wait offshore for the moon to rise, then count the hours until the tide would be right for safe entry. This knowledge was practical, essential, sometimes life-saving. Lunar cycles shaped early navigation and coastal settlement, influencing where harbors were built, when ships could sail, and how communities organized their relationship with the sea. Medieval tide tables followed the lunar day, listing the times of high and low water for each day of the lunar month. These tables were among the earliest examples of scientific prediction, using past observations to forecast future events with reasonable accuracy. They weren't perfect. Local weather and winds could modify tides in ways the tables couldn't account for. But they were good enough to be useful, and they represented a hard-won understanding of a natural phenomenon accumulated over centuries of observation. Monasteries kept tide tables. Port authorities kept them. Ship captains kept them. They were valuable information, sometimes closely guarded, giving those who possessed them an advantage in maritime trade. The rhythm of tides influenced daily life in coastal communities in profound ways. Rotating work schedules emerged from tidal timing, because many activities could only be done at certain stages of the tide. Fishermen set their nets at specific tidal states. Longshoremen loaded and unloaded ships when the tide was high enough for vessels to reach the docks. Foragers collected shellfish and seaweed at low tide when the rocks were exposed. These activities couldn't follow the solar day because tides don't follow the sun. They follow the moon, arriving 50 minutes later each day. So coastal work schedules became more complex, shifting daily to match the tides. People learned to sleep when the tide allowed, to work when the tide demanded, living by a rhythm that was neither purely diurnal nor purely nocturnal but something in between, dictated by the moon's stately progress across the sky. This tidal rhythm shaped culture, language, and tradition. Coastal communities developed a relationship with time that was different from inland agricultural societies. They were more attuned to the moon, more aware of its phases and position. They coined phrases and metaphors drawn from tidal experience. They told stories about the sea and its moods, about the dangers of being caught by a rising tide, about the opportunities revealed when the water retreated. Children growing up on the coast learn to read the tides as automatically as they learn to read the weather, understanding intuitively what inland children might never grasp, that the ocean breathes in and out, that its breath follows the moon, and that life along the shore means living in harmony with that breath. Even today, in an age of precise tide predictions and atomic clocks, the fundamental truth remains. The tides follow the moon. They rise and fall on its schedule, not ours. Coastal airports, bridges, and ports still plan around tidal windows. Recreational boaters and kayakers check tide tables before venturing out. Surfers know which tides produce the best waves at their favorite breaks. The connection that ancient observers noticed thousands of years ago is still relevant, still practical, still woven into the fabric of coastal life. The moon governs the tides govern access to and from the sea, and anyone who lives or works near the ocean must acknowledge that governance. It's a relationship older than civilization, older than our species, a bond between earth and moon written in the rising and falling of water, visible to anyone who cares to watch and wait. The moon's gravitational pull doesn't just move water. It orchestrates life. Tides strongly influence marine ecosystems in ways that reach from the smallest plankton to the largest predators, creating rhythms that countless species have adapted to over millions of years of evolution. The tides are not just a physical phenomenon that organisms must tolerate. They're a temporal framework that life has learned to exploit, a reliable cycle that provides cues for reproduction, feeding, migration, and survival. The ocean pulses with the moon's rhythm, and life pulses with it, synchronized to the twice-daily rise and fall of water in ways both obvious and subtle. Many species time spawning to lunar tidal cycles, releasing eggs and sperm at moments when conditions are most favorable for the survival of their offspring. This timing isn't arbitrary. Spring tides, with their higher water levels and stronger currents, can carry eggs and larvae farther from shore, dispersing them more widely, reducing the risk that predators will find and consume them all. The full and new moons that trigger spring tides also provide a reliable signal, a clock that works the same way every month, allowing populations spread across vast areas to synchronize their reproductive efforts. When everyone spawns at once, predators become overwhelmed. They can't possibly eat all the eggs or larvae. Some, perhaps most, will survive simply because there are too many targets for the predators to handle. This is predator satiation, and tidal timing makes it possible. Corals synchronize mass spawning with full moons in one of the ocean's most spectacular displays of reproductive coordination. On certain nights following the full moon, usually at specific times of year when water temperature is right, entire coral reefs release their gametes simultaneously. Billions of eggs and sperm bundles float to the surface, creating an underwater snowstorm in reverse, pink and white packets drifting upward through the water column. The timing is precise, often occurring within the same hour across hundreds of kilometers of reef. Scientists believe the lunar cycle provides the primary cue, with the full moon triggering hormonal changes in the coral polyps that lead to spawning several nights later. The result is a brief window of opportunity for fertilization, eggs meeting sperm in the open water, creating the next generation of corals that will eventually settle and begin building the reef anew. Fish activity increases during spring tides across many species and habitats. The stronger currents bring more food, more oxygen, more opportunity. Predatory fish become more active, hunting in the swifter flows where prey fish are disoriented or swept along. Reef fish venture farther from their hiding spots when the tide is running strong, feeding aggressively before retreating to shelter. Even deep-sea fish, living far below the reach of surface waves, show patterns of activity that correspond to tidal cycles, responding perhaps to subtle changes in current or pressure that penetrate to the depths. The exact mechanisms aren't always clear, but the pattern is consistent. When the tides are strong, fish are active. When tides are weak during neap periods, activity declines. Zooplankton migration follows semi-diurnal tides, adding another layer of vertical movement to the daily vertical migration these tiny creatures already perform in response to sunlight. Many zooplankton species rise toward the surface at night to feed on phytoplankton, then descend to deeper, darker water during the day to avoid visual predators. But superimposed on this daily cycle is a tidal cycle. Zooplankton often adjust their vertical position based on tidal currents, rising during certain tidal phases and sinking during others, perhaps to control their horizontal transport, to avoid being swept into unfavorable areas, or to take advantage of currents that will carry them toward better feeding grounds. The result is a complex three-dimensional dance, zooplankton moving up and down through the water column in response to both sun and moon, optimizing their position hour by hour. Crabs use lunar cues to forage and hide, timing their activity to avoid predators while maximizing feeding opportunities. Many crab species are more active during high tide when they're safely submerged and can move freely. During low tide, they retreat into burrows or hide under rocks, avoiding birds and other predators that hunt in the exposed intertidal zone. Some crabs spawn during spring tides, releasing their larvae when the stronger currents will carry them offshore quickly. Fiddler crabs, those small crabs with one oversized claw that inhabit mudflats and marshes, synchronize their activity to the tides so precisely that you can predict their behavior just by knowing the tidal state. At low tide, they emerge from their burrows to feed on the exposed mud. As the tide begins to rise, they retreat underground, sealing themselves in to wait out the flood. This happens twice a day, every day, year after year, a rhythm so deeply ingrained that even if you take fiddler crabs into a laboratory far from the ocean, they continue to show activity patterns that correspond to the tides that would be occurring at their home beach. Birds and predators exploit tidal timing for feeding, learning the schedules that govern their prey's behavior. Shorebirds time their arrival at beaches and mudflats to coincide with falling tides, following the water's edge as it retreats, probing the wet sand for worms, clams, and crustaceans that burrow just beneath the surface. Herons and egrets stand in shallow water during rising and falling tides, striking at fish that move with the current. Even terrestrial predators like raccoons and foxes learn to visit the shore at low tide, scavenging stranded fish and invertebrates or hunting in tide pools. These predators don't have an internal tidal clock in the way that some marine species do, but they're smart enough to learn the pattern, to recognize that low tide means food, and to adjust their behavior accordingly. The reason so much life concentrates around tidal cycles is simple. Tides transport nutrients across intertidal zones, creating extraordinarily productive ecosystems. Each rising tide brings plankton, organic debris, and dissolved nutrients from the ocean into estuaries, marshes, and mangrove forests. The water floods across mudflats and through seagrass beds, delivering food and fertilizer. When the tide falls, some of that material is left behind, trapped in pools, filtered by oysters and mussels, or absorbed by marsh plants. The next tide brings more, a twice-daily delivery system that makes intertidal zones some of the most fertile ecosystems on the planet. Estuaries, which experience the full influence of tides, are among the most productive environments on Earth, rivaling tropical rainforests in terms of biomass production. Stronger tides increase prey availability for predators at multiple levels of the food chain. The enhanced mixing that comes with spring tides brings more nutrients to the surface, spurring phytoplankton growth. More phytoplankton means more zooplankton, which means more small fish, which means more large fish, more seabirds, more marine mammals. The effect cascades upward through the ecosystem. Fishermen have known for centuries that spring tides often produce better catches, not because the tides themselves attract fish, but because the entire food web responds to the moon's cycle. When the tides are strong, life is more abundant, more active, more accessible. Entire food webs respond to lunar rhythms in coordinated waves of activity. The moon waxes and wanes, the tides strengthen and weaken, and life follows. It's not just individual species responding in isolation. It's ecosystems responding as integrated wholes, with timing that cascades from primary producers to top predators. The phytoplankton bloom following spring tide mixing supports a pulse of zooplankton reproduction, which supports a surge in larval fish survival, which attracts larger predators, which draws seabirds to feeding frenzies. These patterns repeat monthly, overlaying the daily rhythms of sunrise and sunset with a longer lunar cycle. For marine life, time is measured not just in days but in tides, not just in months but in lunar cycles. The moon is more than a light in the night sky. It's a conductor, and the ocean's ecosystems are its orchestra, playing a symphony that has been performed for hundreds of millions of years, since the first complex marine life evolved to recognize and respond to the tides. And tonight, as you lie here listening, that symphony continues, invisible but ceaseless, life and water moving together to the moon's ancient rhythm.